a generative prior, and it will be presented by Oscar Leong.
Generative models have showcased the impressive ability to create realistic samples from highly complex image classes. Now, some common examples are celebrity faces and bedrooms, but some recent results have been able to create generative models that can generate samples such as MRI scans, cells, and human fingerprints. So at this point, we're all quite familiar with what generative models can do in image generation, but today's talk is going to focus on how we can exploit them in image recovery problems, and how they've already pushed forward the state of the art in theory and in practice. And so in today's talk, I'm going to discuss a bit about their empirics and a little bit about why they seem to be performing so well. And in particular, I'm going to try to argue that generative models provide lower dimensional priors that can be directly and efficiently exploited. And then I'm going to discuss how this has the potential to impact the imaging sciences and how experimental scientists can use deep learning and generative models to solve their own tasks. And so before I go into this point about their empirical success, I want to first discuss what exactly is an inverse problem. And so in an inverse problem, we want to recover an image x naught from some transformed version of it, which I call phi of x naught. So here, phi of x naught are our measurements, and each entry of phi of x naught is a single measurement. And so some common examples of these inverse problems from image processing are denoising, inpainting, and super resolution, where we want to recover a clean image from a noisy version, a masked version, and a low resolution version. And so two important problems that are closely related that I'm going to be focusing on today are compressed sensing and phase retrieval. So compressed sensing, we want to recover an image x naught from its low dimensional linear projection. So you can think of phi as a fat matrix with fewer rows than columns. And so phase retrieval is a nonlinear version of this problem where we only get to see the absolute value of these linear measurements. And so how exactly we're going to use generative models to solve these problems, we're going to use what's called a generative prior. And so a prior is our previous knowledge about the image of interest that we can exploit to recover it with fewer measurements. And so under a generative prior, what we want to do is we want to find the image in the range of our generative model that best approximates our image of interest. And so when I talk about generative models, I'm going to be focusing on latent variable models such as VAEs and GANs. And so in order to utilize this approach, what you first need to do is train a generative model to output a certain image class. So these are images that your image of interest looks like. And then you want to find the image in its range that best fits your measurements. And so what you can do is you can directly optimize over the range of your generative model via empirical risk minimization. So I want you to notice a couple things about this objective function that you see here. So the first is that we're optimizing over the input to the generative model. And also, due to the nonlinearity of the generative model, this is going to be a non-convex optimization problem. And in addition, I stated it with a generic phi map here. So this formulation is actually quite versatile, allowing the use of a lot of different measurement modalities. And so just to give examples of where these types of generative models have provided state-of-the-art performance, so we talked about these previous common image processing problems, denoising, inpainting, and super resolution, but they also shown great performance in compressed sensing. So for example, results from Bohr et al. From UT Austin show that you can actually recover images with 5 to 10 times less measurements than sparsity-based methods such as lasso. And in addition, Mardani et al. Show that you can actually do MRI imaging with the speed up of 2 orders of magnitude, utilizing GPUs and convolutional nets. Okay? So based on these empirics, we want to try to understand why these generative models tend to perform so well. I want to make the argument that it's due to the fact that they provide lower dimensional priors that can be directly and efficiently exploited. And so what exactly are we comparing them to? We're comparing them to sparsity-based models that use a sparsity prior. And what exactly do I mean by a sparsity prior? So natural images are nearly sparse with respect to a wavelet basis, meaning that in that basis, they can be approximated by something sparse. So as an example, you can consider the following two images here. So the image on the left is a photograph, while the image on the right was created by taking a wavelet transform of the image on the left, keeping only 10% of the largest wavelet coefficients. And as you can see here, there's still a high fidelity between the two images, even though the image on the right only has 10% of the wavelet coefficients. And so this notion of sparsity led to a lot of advancements in image recovery problems, in particular for the field of compressed sensing. So sparse compressed sensing led to a speed up of MRI imaging by a factor of 10 when it was first conceived, and offers its own theoretical guarantees. But one issue with sparsity is that it may be too broad of a prior to actually exploit the low dimensionality of our data. So just as a thought experiment or a toy example of this, you can consider the following here. And so suppose we had an image class consisting of images of a single train, the same train, moving in a single direction. Right? So all these images are of the same train moving in a single direction on this railroad. So there's really only 1 degree of freedom in this image class. So we could think of this image class as living on a one-dimensional manifold in natural image space. So here the one-dimensional manifold is this line that you see here in red, and natural image space is this gray object, which is the natural image manifold. And so this single image lives on a particular point, but what sparsity-based methods will say is, well, this image is sparse with respect to a certain basis, but it wouldn't try to exploit any further information about how it relates to the image class. But what's the best way that we know how to approximate these low-dimensional manifolds was with the generative model. And so we can use deep learning and these generative models to actually exploit and understand the low-dimensional structure of our data. Okay, so in addition to having lower dimensional representations, generative models also allow for direct optimization. And so just to draw a comparison, for sparsity-based methods, suppose we wanted to find the sparsest solution to a linear system of equations. So in this case, phi here is a matrix. And so what you could do is you could minimize the L0 norm subject to fitting your measurements. So L0 norm counts the number of non-zero entries in your vector. And so due to the computational intractability of the L0 norm, you can do a convex relaxation where you instead minimize the L1 norm, which is the convex surrogate for sparsity. And so this is great when you have linear measurements, but this may not be possible with nonlinear measurements. And so what you can do with the generative model instead is you can directly optimize this optimization problem where phi can be linear or nonlinear. And also, when you're looking at this convex surrogate formulation here, if you have nonlinear measurements, penalizing the L1 norm of your solution has shown to fail in certain problems, or appears to fail in certain problems. Now that's going to be the focus of our attention today in the compressive phase retrieval problem. So in this problem, we want to recover an image x naught from some nonlinear measurements, which are the absolute value of linear measurement. And so here we have m nonlinear measurements where each entry of the absolute value of a times x naught is a single measurement. And there's actually an open problem in the phase retrieval community, which is there is no known efficient algorithm to recover an S-sparse signal from order S generic measurements. And by generic, I mean that the matrix A has IID Gaussian entries. And so there are some methods that provably cannot beat order S squared by direct L1 penalization. But what we show is that under a generative prior, you can actually get sample complexity that's linear in the latent code dimension. And so that's what brings us to our formulation of the problem, which is phase retrieval under a generative prior. So here, we have these nonlinear measurements, the absolute value of A times x naught. We want to recover the image x naught by assuming it's the output of a generative model. So in order to recover the image, we can recover the original latent code corresponding to it, from which we can get the image back by just applying the generative model. And so we can do this by finding the best image in the range of the generative model that best fits our measurements by minimizing this empirical risk minimization problem. And so what we show is that actually this objective function has favorable geometry for gradient methods with sample complexity that's linear in the latent code dimension. And so what we show is that the objective function has a strict descent direction outside of neighborhoods of the minimizer and a negative multiple thereof with high probability, so long as the following assumptions are satisfied. So if the number of measurements are linear in K, the network layers are sufficiently expansive, so they grow in a certain way, and the measurement matrix A and the weights of our generative model have IID Gaussian entries. So if we take a step back and think about why did generative models perform so well, was that they have lower dimensional representations, so meaning that this K parameter can actually be lower than sparsity in some cases. And also, this can be directly exploited, so that's by the empirical risk minimization problem that we showed, which optimizes over the range of their generative model. It can also be efficiently exploited based on the fact that we can get sample complexity that's linear in the dimension of K as opposed to something quadratic. And there's actually exciting work being done at this conference by a group out of MIT, from Ma et al., that showed that a result like this can be shown in the linear case with actually convolutional layers as opposed to fully connected layers. And so we also looked at the case when we want to recover images from the MNIST data set. And so here are just qualitative examples of recovery. And so we used a variational autoencoder, and we compared our method to 3 sparse phase retrieval algorithms. And we showed that with only 100 measurements, we can semantically nearly recover all of the images, while the sparse phase retrieval methods are unable to do so. So now that we've discussed a bit about their empirical success along with why they seem to be performing so well, I want to talk about how this has the potential to impact the imaging sciences and how we can provide a new workflow for experimental scientists. And so this new workflow really just involves 3 simple steps. So the first would be that you would create data sets of images that are relevant to your problem domain. So for example, for phase retrieval, this could be electron density maps, or this could be MRI scans. And then once your data set is trained, once you obtain this data set, then you can train a generative model to output these types of images. And then once you have this trained generative model, you can use it as a prior by collecting your measurements and then solving the optimization problem that we mentioned before. And there's actually already been work done in trying to create these types of data sets. And so here are just some examples of that. So the first image that you see on top is actually a screenshot from the Protein Databank website, where it has thousands of images of these crystallographic structures that you see in X-ray crystallography. And in addition, NYU and Facebook just teamed up and made a new data set for MRI imaging. And so this is actually something that happened within the past week or so. So this is definitely an avenue of research that's gaining traction, and that's definitely important for work to come. And so just to reiterate some of the main points of the talk that we had today, were that generative models have provided state-of-the-art performance in these imaging inverse problems, and part of the reason for that is because there are lower dimensional priors that can be directly and efficiently exploited. And we saw a specific case in point of that with the phase retrieval problem, where we can get sample complexity that's linear in K. In addition, we talked about how this could potentially provide a new framework for scientists in experimental imaging by utilizing these deep learning models and generative models. So I hope to see you later on at our poster after this session, and thank you for listening.
Time for questions? So let me begin with one. Much of what you presented is experimental, but when we look at sparse recovery, there is usually a lot of theory as to when can you recover the true signal. Can you comment as to whether there are at least some specific cases for which you also can have some guarantees of recovery?
So guarantees of recovery in terms of sparse recovery? Mm-hmm. Yeah, so in terms of, for example, with compressed sensing, the problem that we mentioned here before, you can actually also guarantee recovery in case you have a linear phi map here. You can actually guarantee recovery with order S measurements. In terms of our model that we showed here with the generative prior, so our formulation actually talks about the geometry of the objective function, but we haven't proven that we can actually get the signal yet. Mm-hmm. So we do give an algorithm to actually try to recover the signal, but further work needs to be shown that this algorithm actually converges to the true signal that you're looking for.
Now, if I understand, your results guarantee the existence of a descent direction when you're far from the true signal. Mm-hmm. So what if the point at which you are at is not a differentiable point?
So actually we give a descent direction that has an explicit formula regardless if the point is differentiable or not. So what our theorem really guarantees is that at any point outside of these neighborhoods, there is a direction I can give you where you will have a point of lower objective value.
So hopefully someone has a question at this point. No? All right. So let's thank the speaker. So the next talk is a spotlight. It's entitled Global Geometry of Multi-Channel Sparse Blind Deconvolution on the Sphere by Yang-Jun Lee and Yoram Bressler, and the talk will be given by Yang-Jun Lee.
Thanks for the introduction. Good morning. Today I'm going to present t-divisor multi-channel sparse blind deconvolution on the sphere. Well, multi-channel sparse blind deconvolution arises in a variety of applications, ranging from opportunistic underwater acoustics to reflective seismology to functional MRI to super resolution fluorescence spectroscopy. And it's essentially the problem of recovering an invertible signal F and multiple sparse filters Xi from their circular convolution Yi. Basically, given a bunch of Yi's, we need to recover both F and Xi's. Despite the previous efforts in solving this problem, a guaranteed algorithm for essentially unconstrained F is still an open problem. Well, today we're going to present a new solution. Well, given that F is invertible, it's natural to find an inverse filter H that is a shifted and scaled version of the inverse of F, which will produce sparse outputs at the end of this diagram. But when we try to solve the problem P0, we notice that it's a non-smooth function that's very challenging to solve. So instead, we're going to solve a smooth surrogate of the objective function. For those of you who are familiar with compressed sensing, a very popular surrogate for sparsity is L1 norm. Here, we're going to use an even smoother objective, which is maximizing the spikiness of the signal, the L4 norm, on the unit sphere. We'll show that the solution of this smooth objective will be signed and shifted versions of the ground truth. Given our main theorem says that when Xi's follow a Bernoulli-Rademacher model, and we have a sufficiently large number of channels, Xi's, then every local minima of the objective function is a signed and shifted version of the ground truth. And we also show that near the local minima of the objective functions, the function is strongly convex, and near other stationary points, which we call strict saddle points, they have negative curvature. Here is a pictorial demonstration of the objective functions, the norm of the gradient, and the smallest curvature. We can see that only around the shifted and signed ground truth is the objective function strongly convex. Well, given these nice geometric properties, we'll give a theoretical guarantee of a simple first-order algorithm. It's called manifold gradient descent, which essentially takes a gradient step along the tangent space of the unit sphere and do a retraction, which is projection back to the unit sphere. And this is a very low time complexity algorithm. And we show that given the geometric properties we have, and simply using random initialization and fixed step size, manifold gradient descent can converge to a local minima, which again will be a signed and shifted version of the ground truth. And we achieve very high accuracy after a polynomial number of steps. Even better, when we use Monte Carlo simulation, we can show that better than our uniform guarantee, which works for the worst case. In Monte Carlo simulations, the number of channels we need grows actually linearly with the size of the problem and the sparsity level, and has very weak dependence on the conditioning of the problem. And it converges much faster than a polynomial number of steps, only converges around dozens of steps. And we also demonstrate that our algorithm can be applied to super resolution fluorescence microscopy, which basically recovers a sequence of sparse images, blurred version of sparse images. And we show that under our blind deconvolution algorithm outperforms the non-blind deconvolution algorithm when the kernel is slightly miscalibrated. Thank you.
The next spotlight is theoretical linear convergence of unfolded ISTA and its practical weights and thresholds. And the talk will be given by Xiaodan Chen.
Thank you for introduction. Hello, everyone. The paper I will talk about today is about the LISTA, or learned ISTA. Specifically, its theoretical linear convergence and practical weights and thresholds. So our paper proposes a new fast algorithm to solve the sparse linear inverse problem. We want to recover sparse vector x star from its noisy linear measurement B. So we propose two improvements on the LISTA, which was originally proposed by Greger and LeQuin in 2010, and some related works. Our model learns less than half of parameters than that of original LISTA, so we have a faster training and more stabilized training process. And we also add the sport selection technique for better and faster recovery. And we also provide linear convergence and robustness analyses. Therefore, our method has theoretical guarantees. To review ISTA, we can see it actually takes a recurrent form of iterations. In each iteration, it has two matrix multiplications followed by a self-thresholding function, which is based on the optimization. And there are two parameters to be tuned, and which is easy to tune. And on the other hand, the LISTA, or learned ISTA, uses different matrices and different thresholds in different layers. And these parameters are chosen by stochastic optimization. Unlike in neural network, and this stochastic optimization can be approximately solved by synthesizing a large number of input-output pairs and update the parameters using backpropagation. And to compare ISTA and LISTA, ISTA is slow to converge, but it's easier to tune, and it is free of training. And for LISTA, it is fast, but it is difficult to train. So our methods actually improve the training of LISTA. Specifically, we first introduced the coupled LISTA, where we couple the two matrices in each iteration of LISTA, because we can theoretically show that if we want xk to converge to x star in the limit, we must have this identity to hold at least asymptotically, which can also be corroborated by empirical observations. And based on that, we proposed the coupled LISTA with support selection technique. The support selection technique actually supports a portion of large coordinates in each iteration of LISTA and let them bypass the self-thresholding activation. And this idea actually comes from the linearized Bergman iteration, or the kicking technique, and also the fixed point continuation method. Theoretically, we can show that both of these methods, the coupled LISTA or the coupled LISTA with support selection, have robust global linear convergence. That is to say, we can actually find a sequence of parameters such that the coupled LISTA converge to the ground truth solution in a linear rate, in a linear convergence rate, and the support selection can further help the algorithm to improve the convergence rate and also help to find a better recovery. And empirical results show that the coupled LISTA can have more stabilized intermediate results, and the reduced parameter space will not hurt the final recovery performance. And the coupled LISTA with super selection can have, from this figure, we can see it can have a significantly better final recovery performance and also a much better convergence rate. And hope to see you at the poster session, and thank you for listening.
So this is the last talk of this session. The title is Spectral Filtering for General Linear Dynamical Systems. And the talk will be given by Cyril Chiang.
All right. Hi, good morning. I'm Cyril Zhang, a grad student at Princeton and intern at Google AI. I'll present our most recent result on LDS prediction, which is joint work with my wonderful colleagues Elad Hazan, Holden Lee, Karan Singh, and Yi Zhang. All right, so we're going to consider a linear time-invariant dynamical system with a hidden state in discrete time. It transforms a time series of inputs, ut, into a time series of outputs, yt, or responses, by linear dynamics. And each of these two equations might be noisy. We might have some internal process noise, which lingers in the hidden state over time, or just noise on the observations. Linear state space models are considered everywhere, from robotics to meteorology to finance, wherever we have to deal with repeated continuous measurements of an evolving system. And more recently, LDSs have seen some renewed interest as they appear as the simplest non-trivial settings when you strip down reinforcement learning problems or recurrent neural nets. So the task we'll consider today is online prediction, which some of you might know as nowcasting. At each time step here, the learner has seen all the inputs and outputs so far, is asked to predict the next output of the system, then finally observing the ground truth response yt. So note that the system generating the yt's doesn't need to be an actual LDS, but we'd like our predictions to suffer a mean squared error comparable to those made by the best possible LDS in hindsight after fitting the data from the entire trajectory. Okay, so here's the usual recipe for doing prediction from an LDS. Suppose we had in hand the dynamical matrices ABCD. Remember, this is not our setting at all. And say we had a prior for the initial hidden state. Well, in the 60s, Rudolf Kalman showed that under a Gaussian noise model, one can recursively propagate the best linear unbiased estimator, a technique which now bears his name as the Kalman filter. It's hard to overstate how influential the Kalman filter has been over the years. It's in the source code of the Apollo lunar lander, if you go take a look at that. But we often don't have these matrices in hand, like in our setting. And as it turns out, learning ABCD from data is kind of an annoying problem. It's a hard non-convex optimization problem for which there are countless heuristics out there in the world, like expectation maximization. So in the absence of knowledge about the system or any recoverability assumptions, we'd like to bypass system identification. We'd like to predict as well as in LDS without learning ABCD. So to this end, as a warm-up, let's first consider a system whose hidden state mixes or decays rapidly. So then beyond log 1 over epsilon iterations, or you can think of this as half-lives ago, no input could have had more than epsilon influence on the current output. So when writing down the system's impulse response, its linear dependence of yt on the past inputs, we can truncate effects from the distant past. And on the more recent past, we can fit an autoregressive model. So up to epsilon, this still captures all possible dynamics of an LDS, as long as we assume that it mixes. And the only price we've paid is that the autoregressive model has forgotten the nonlinear constraints between these matrix blocks. But under mixing assumptions, we didn't expand this parameterization by too much. It's only a modest overparameterization. And now, what we've gained for the price of a few more parameters is that we can learn these dynamics improperly by linear regression or ordinary least squares. It's now a convex program. Okay, so that's our story when the system mixes quickly. So now I'll state our result, which handles a more interesting general case. Our prediction is, our algorithm is going to make predictions that compete multiplicatively with the best LDS with polynomial constants, and it runs in polynomial time. And unlike other provable methods we've been able to find, it doesn't degrade with the mixing time of the system, which usually appears as a condition number in these sorts of results. Recall that our setting has limited us to a single trajectory without mixing, with no restarts of the system allowed. And this result generalizes and extends the spectral filtering technique and paper that Elad, Karan, and I presented at last year's NeurIPS in Long Beach. Okay, so to understand how our new result works, let me give a quick recap of last year's paper. we proved that although the response of an LDS with a symmetric transition matrix can depend on the distant past, it can only do so in a low-dimensional way, in particular through convolutions by a small bank of filters. And these filters can be computed from the top eigenvectors of a certain deterministic Hankel matrix, which we know at the beginning of time, independent of the data. I guess the upshot is a mild overparameterization, just like the autoregressive model we considered earlier, that works for systems that don't necessarily mix. So this gives rise to a provable and very efficient algorithm for online sequence prediction, but we had to compete with the best symmetric LDS. So I guess the top comment we got after presenting that paper was, what about non-symmetric LDSs? And I guess at the time we were like, we're working on it, but now we have a more general result for all diagonalizable transition matrices. The problem is when A is symmetric, there's no such small basis of filters anymore. The structural result from the previous slide didn't hold. The dependencies truly are not so low dimensional. But we showed that by adding on top of the previous result an autoregressive model on the past few inputs and outputs, on the order of the dimensionality of the system we'd like to compete with, as well as a second convex relaxation that has nothing to do with the first one, an L1 relaxation of the sparsity of phases of the complex eigenvalues of the transition matrix. It gives us a more general analogous result for all LDSs with diagonalizable A. So as with our previous paper, the structural result is able to reduce the prediction problem to online convex optimization. So before in the previous paper, we would predict from the span of the input time series convolved with these deterministic eigenvector filters. I said they were deterministic, so here they are. And our new structural result can be seen as, well, convolving the inputs with a much larger bank of filters, which are just the original ones, pointwise multiplied or phased by complex exponentials. Okay, so I'll give just one slide on the kind of mechanics of how the new paper works. So the structural result, as I just said, tells us that our prediction should lie in the span of some particular set of vectors. I'll call this hypothesis class, as we do in the paper, a pseudo-LDS. So it remains to discuss from which pseudo-LDS we should predict at each iteration. So in the previous paper, we could just use online gradient descent or ridge regression, if you like. For general LDSs, it's a little less straightforward to come up with the regret minimizing prediction rule. The huge parameter count in a pseudo-LDS should normally degrade the sample complexity, but we're actually able to regularize by the L1 relaxation of the sparsity of phases. That is, like looking at the previous slide, even though there are many filters to combine the signals of in a pseudo-LDS, we should only take a combination of a small set of them. So this allows us to use the follow the regularized leader algorithm from the online learning literature with a certain mixed matrix norm regularizer on the filter terms. And so the main result that our predictions compete with the best LDS in hindsight just follows from regret bound versus the best pseudo-LDS in hindsight, combined with the fact that we noted earlier that pseudo-LDSs capture dynamics that are more expressive than the set of LDSs. And note finally that this reduction to online convex optimization allows our algorithm to be robust not just under statistical noise, but under adversarial perturbations to the system. All right, so that's all I have. Please stop by our poster, number 167, to which I will shortly run. I'll leave this up, and I'm happy to take questions until then.
So please, if there are any questions, there is a mic on each side. We have plenty of time for questions, so. Could you go to the mic, please? Or if we could get the mic to him.
So is your regret expression optimal, or if not, how far are you from a lower bound?
Yeah, good question. So it's not going to be a statistically optimal regret bound. In this paper, we're only focused on just achieving kind of a polynomial numerator in the regret bound. It seems that if you actually want to reach the statistical limit, which is like the number of parameters of the original LDS, it seems like you have to do system identification at some point, and it's a very interesting open problem to actually sharpen the statistical bound while maintaining computational tractability.
Hello? Can I ask a question over here? Here. Yeah, thanks for the great talk. And I've just one clarification question. So in your formulation, you truncate the distance path to make an epsilon accurate prediction of future. Wouldn't that gives you a linear regret of like epsilon t kind of thing?
Oh, all right. So I was being a little glib about that. So when I'm truncating the path, that's sort of the warm-up slide. We're not actually truncating the past in our paper, and indeed you can actually view our structural result as an autoregressive model of the order the entire time horizon restricted to a certain subspace. Yeah.
Thanks.
Could you reconstruct the state matrices from the filters that you get?
Yeah, we have tried very hard to do that. It still seems like some hardcore non-convex problem, even when you've kind of found these pseudo-parameters. Furthermore, there's no guarantee that you actually recover the, say, autoregressive parameters that correspond to the system dynamics in this improper learning scenario.
We still have 3 more minutes for questions. So I have one question. The literature on system identification, maybe from the 70s and 80s, was all based on somehow from the data computing a Hankel matrix and then factorizing it to get the structure. And whether you could do that depended on whether you knew the inputs or not and whether they were stochastic or not. So it seems to me that there are some connections that pertain relaxing all of the internal constraints. And in their case, they also had theoretical results. So I just wanted to get an understanding of whether you could comment relative to the classical system identification literature.
Yeah, great question. This is something we've kind of been digging through the literature about for a couple of years now. Right, so in system identification, I guess if you Google like linear dynamical systems Hankel matrix, you'll see like our results and like a bunch of results on constructing this block Hankel matrix of like, I guess it's called realization of the system. I think you need the system to be very close, first of all, to a true LDS, whereas our result is kind of agnostic, and the Hankel matrix, of course, isn't constructed from data. So we're not able to find an explicit relationship here. And indeed, people use these sort of like Hankel matrix derived subspace identification methods as an initialization for EM. We think this doesn't get kind of comparable guarantees as where we get an agnostic learning guarantee. I guess the other thing is that these sort of explicit sysid methods are statistically brittle, which I didn't really mention in the talk. You sort of need recoverability assumptions on the system, as well as these persistent excitation assumptions on the input design. We don't require any of that, so I think it's just kind of, we're still not able to find any kind of direct cross-pollination, even though there are Hankel matrices appearing in both.
Okay, let's thank the speaker. And this answers. So you're welcome to go to the expo or to the poster session. Thanks.